be aware of that. So we had a couple things due today. We had a quiz. They all look at me like that. Yeah, what? So if you have your quiz, please hand it up. There's also a lab due. You had lab last Thursday. Yeah, okay. If you haven't handed it in, some people emailed it to me, some people gave it to me already, but whatever you have, please pass up. So that said, does anybody have any questions on the quiz? Yes?
Oh, it was just regarding a question to,
Okay.
yeah,
Yeah, show me the question.
I think I kind of went into too much detail, I guess. Hopefully that's
All right, so which question,
question two.
two, okay. Question, calculate the frequency?
Yeah.
Okay. Calculate the frequency for light.
What's on that? Does it
Green
put
laser
the quiz already? You
pointer.
put them already?
Wavelength is 540
Yeah.
nanometers. Anybody get that one? Get rid of all this good fiber optic stuff.
I don't want the quiz. Keep that.
Okay, so we have a green laser pointer. What we know is the wavelength, lambda, is 540 nanometers. Nanometers means what?
10 to the
10
minus
to the 9.
So we have, which is the same, 540 times 10
to the 9.
to the minus 9 meters. Okay? So we have an equation that relates frequency, speed of light, and wavelength. You guys remember what that was? Remember? C is equal to
63?
Yeah, a lambda
wavelength
or
times frequency, right?
yeah.
Good. So we're looking for the frequency here. So if we solve this equation for frequency, we just divide both sides by lambda, we get frequency is equal to c, speed of light in the vacuum.
Wavelength.
What's that? Yeah, divided by the wavelength. So if we plug our numbers in here, we get 3 times 10 to the 8th meters per second, divided by lambda, which is 540 times 10 to the minus 9 meters. The reason I'm expressing this in meters is because I have meters per second in the numerator. Okay, denominator has to be the same, these cancel out. Part of the reason I do these equations is to make sure that you understand the unit conversions. Okay, make sure you always show your units on quizzes. Don't give me just a number for an answer. But if you plug in the numbers here, anybody have a solution for this? Can I crank it out?
It's 555 times 10 to the 12.
555 times 10 to the 12 units. When I cancel out meters here, what's left if I have meters divided by second and I get rid of the meters?
Per second.
This gives me the unit of 1 over seconds, which is the same thing as saying hertz. Okay? So 555 times 10 to the 12 hertz. If we want to use the metric prefixes, 10 to the 12th is what?
Tera.
Tera. So this is the same as saying 555 terahertz, which is a whole bunch of hertz.
Can we do number 3?
Yeah. Number 3 says calculate the energy in joules for a photon of wavelength 488 nanometers. Okay. So let's see, 3. So what's given is the wavelength. When you're solving these problems, always write down everything that's given. So what do I know and what do I need to figure out? So the wavelength is 488 nanometers. Okay. What else do I know? In order to solve, I mean, we're looking for energy, right? What is energy? There's an equation for energy. Yep. E is equal to H times F. Okay. What's H?
Planck's constant.
Planck's constant. Okay. So what's that?
Energy in electron volts.
Joule, it asked for it in joules, so we're gonna use the joules. But you guys know what this number is?
It's 6.625 times 10 to the 30.
34.
6.625 times 10 to the minus 34 joule seconds, okay? So that's a given, so we know that, all right? But is this the right equation, given that we have wavelength?
We have to find the F.
Okay, we need to find out. But there's another equation that relates energy to wavelength. Chris?
It's Planck's constant times the speed of light divided by the wavelength.
Right. So we can also express energy in joules as H times, using this same relationship here, F is equal to C over lambda, you plug that in here. So we have H times C over lambda. Okay? So we know what Planck's constant is, we know what the speed of light is, we know what the wavelength is, we can go ahead and crank out what that energy is. So if we plug the numbers in, we get 6.625 times 10 to the minus 34 joule seconds times, I'm running out of whiteboard space here, 3 times 10 to the 8th meters per second on top, and on the bottom we have 488. Okay, nanometers means times 10 to the minus 9 meters. Let's collect our units. Meters cancels out, meters cancels out. Seconds over here cancels out with seconds over here, and all we have left is joules. So if we crank out the number, does anybody have that, punch that out?
4.07 times 10 to the negative 19.
That's what I gotta say.
4.07 times 10 to the minus 19 joules. Everybody else get that? Is that right? Good? Did
I got negative 18.
You got negative 18? Did you get 40.7 times 10 to the minus 18?
Yeah.
Okay, that's the same number.
4.07.
This is, so is it 4.07?
Yeah.
Okay. And this is 18, you said?
Yeah, negative 18.
You guys want to crank this out, see who's right? Pull out your calculators.
So based on, I mean, if we write it differently, but in scientific notation, however, it's still,
As long as your units are correct, I don't care. You know, you could, make, point
Yeah.
0.00000000, you know. As long as the number is right and the units are correct, then it's the same number.
I did, question 2, and I did it differently, but then I redid it on the back page, and I
Okay.
kind of, but, I ended up with 5.6 hertz.
Hertz? Yeah,
Yeah.
right, so you probably forgot to
Right.
consider the nano part of it.
Yeah.
Okay, so,
Let's see, okay, never mind.
I'm sorry?
I did 6.626, not 6.625.
Oh, well, that's just rounding it off, so that shouldn't make too much of a difference. But the 18th, is it 18th or 19th in the answer? It's-
4.07 times 10 to the negative 34. Doing that, everything that you.
Okay. So
I
that's
got
what?
different.
Let me be the tiebreaker.
Yeah.
All right, let's plug some numbers in here.
So just so we can all get it right.
6.625 times 10 to the 34th minus. Depends on the calculator you got.
Yeah.
Yeah. So I'll do that times 3 times 10 to the 8th equals this. And that divided by 488 times 10 to the minus 9 equals. Who said this is right? Who gave me this number? You get the prize, that's right. 4.07 times 10 to the minus 19 joules. Okay. All right, yep.
And I got 407.27 times 10 to the negative 21. So I just rounded over two spaces. and,
What's your, so you said 4 point, oh,
The original number was 407.27 times 10
okay,
to the
4,
negative 21.
so yeah, so the decimal points just,
Yeah.
different calculators put the decimal point different places. So 407 times, if you raise to the minus 21, it's the same as saying 4.07 times 10 to the minus 19. So they're both, it's right, it's correct. Just depends on how your calculator gives it to you. Okay, any other questions? Did you guys get the one with the CIE curve? Yeah? Okay. All right, if there's no questions on that, then we'll continue on. So today we're going to start the chapter on laser safety, but before we start looking at the PowerPoint, just a couple things I want to show you, and I hope this works. So I don't know if you guys have read chapter 1, laser safety, in the book, but if you haven't, start doing that. There's a good website, Coherent General's laser safety website. If you go to work for Coherent General, which is one of the biggest laser companies in the world, anybody, including the secretaries and receptionists, have to take the laser safety course. And it's just a quick video course. It probably takes like 10, 15 minutes to go through it. And just let me show you where that's located. If you go to their website, yeah, okay. So if you see on the left here, laser video, laser safety video, click whatever you like. Let's do the 80 gig one, see if this works. Yep. Okay, so it kind of puts up the screen there. And you get an industrial quality video. Yeah.
That's being qualified back by STCC.
Yep. Buffering, 1% complete. Okay, well, if you do this on your iPhone, it'll probably go a lot faster.
We'll be there by Tuesday.
Yeah, it'll be there.
So needs new fiber optics over Coherent.
Yeah, I think so. Get to work on that, Nick, would you? My wife says eventually her company's motto is we want fiber to the forehead. Just plug it in.
2%.
Yeah. So we're going to let you guys do that. All right, go back to Blackboard. So anyways, if you look at that, go through it. I think there's a little quiz at the end that you can take, just to see if you've paid attention. One of the other things I wanted to point your attention to also is they also have an electrical safety component to this. A lot of times, you're thinking you're working with lasers and it's the light that's going to hurt you. Well, a laser beam, could burn a hole through you. The good thing about a laser beam is that if it burns a hole through you, it also cauterizes as it goes through. So, your chances of survival are much better. But most of the accidents that have caused death in the laser field are caused by electrical problems. Most lasers, and especially industrial lasers, use very high voltage power supplies. And if you're messing with the power supply, you have to know what you're doing. So if you have the opportunity to go through and look at the electrical safety portion of this, this is specifically put together for laser safety, the electrical part of that. So teach you how to discharge big capacitors so you don't get killed. So let's go back to Blackboard and let's see, back to chapter 1.
So couldn't you just simplify it, just unplug it?
What's that?
Couldn't you just simplify it to the point of just unplug it?
No.
No, not with capacitors that big.
Right, you have capacitors that are energy stored. In order to achieve that high voltage, you have to charge up capacitors. And we actually have, as a matter of fact, that's a good question, I'll show you. There are devices called capacitor discharge sticks. And it looks like this. So before you work on anything that has capacitors, whether it's a laser or any other piece of high voltage equipment, you ground one side of this, ground it to the third terminal on your outlet, and then it's got a kilovolt meter on this, and you go through and you touch all the leads on the capacitors to make sure that whatever charge is built up in there gets dissipated through the discharge stick. Okay. Usually, industrial lasers have cabinets with the power supply in it. These are usually hanging right inside the inside of the door on those. So we pass this around. Electrical safety, very important.
I guess it's a good indication of how much power they have if it's measured in kilovolts.
Exactly, in kilovolts. So, okay, so let's. There's also, because we're going to be using laser pointers in lab, in our lab both today and Tuesday. There's no class because Tuesday has a Monday schedule, so we're not going to have this class on Tuesday. But there's some good laser safety pointer safety websites that I want you to look at. Okay, this one here is really good, laserpointersafety.com. There's also one from the FDA that talks about laser safety pointer, and there's another one here, I forget who this one's by, GNP, I'm not sure. With regard to the notes, these are the notes, I'm going to download these in a second. This is chapter 1 from the book, Solutions. There's also a couple of good articles that I posted here. One of them is a journal called Laser Focus World. And if I haven't mentioned this before, there are a number of good trade journals in the laser field that are free. One of them is called Photonic Spectra, and if you go to photonics.com, you can get free subscriptions to this, and they'll send you the journal in the mail. You also have an electronic version of the email to you. But you can also get Laser Focus World, which has all the latest, greatest technology when it comes to lasers, laser application, measurement of light. Very, very informative. And they have an article in Laser Focus World that says, are laser pointers really dangerous? So they talk about some of the hazards that are around laser pointers. And they also have, there's another website here that talks about laser safety equipment. You'd be surprised how much stuff is out there for laser safety. If you decide to go on any of these tours with the companies, you see all kinds of laser safety devices, anything from just signage that goes in the doors to big metal curtains for higher power lasers. If you're in an R&D lab, you know, you don't have to close the entire thing, because if you're the engineer or technician working on the laser, you just want to make sure that people walking by don't get blasted by the thing. So there are all kinds of safety curtains, safety walls that they build, enclosures that are used. The science of laser safety goggles we'll talk about. Hopefully we'll get to that today. But and then we have the laser safety exercise for today, which we'll allow. So let me download this here. This is laser safety, the PowerPoint. Save that. And if anybody, did you guys print this thing out?
I have it saved. No, I
Do
printed
you have it saved? Okay, I made one change to it this morning. I found a better website. On the front page, there's a website that has it's a video clip, a police video of someone, you know, trying to point the laser at a helicopter. Idiots, police helicopter, really. Trying to point the laser at them. But they use their night vision goggles, which I thought was kind of cool because it also
Sorry,
talked
there's
about
the video.
infrared, yeah. But I'm going to show it to you now, just to show. So, before we start this, does anybody recognize this picture? What movie that came from?
War of the Worlds.
Nope. This
It
was,
says Real
it
Genius.
dates me, yeah, Real Genius,
Oh.
back when Val Kilmer was thin, you know. But it was a great movie, came out in the 80s, and I used to make that required viewing for my laser class, because it actually does talk about a lot of laser technology, and some of it's actually accurate, even though the results, and, you know, I have students pick out the bloopers, like, you know, what color's the beam, and does that actually work? Like they have like this, like, I mean, that color right there, just really just shows like a plasma color. It's not really the laser. Any laser that can do that, you wouldn't be able to see because it would be infrared. So, just saying. But there's a little clip here that I thought you'd find interesting from YouTube. It talks about teens pointing laser at an aircraft.
Did something like that just happen?
it. It happens all the damn time.
Yeah.
We're gonna say we have the lasers
right here. We have the subjects, they're on the agenda court right in the middle, like there's a unit thing that's slide by and assist us on this.
Notice the infrared technology.
These guys are continuously getting us here now, so I got 3 of them at the dead end of the court. Okay, running now. Okay, everybody's over. This laser, we're going to stay with the target if we know where the laser is.
The dog.
Yeah.
Serious business.
Guarantee they may contact you.
That's fine, thank you.
Busted.
Just keep walking. About 5 feet, 4 feet, 3 feet, 2 feet, should be right there. Touch to an air gun, I believe.
We're happy to announce our new chapter, Space and Flight.
These global
You went
leaks.
commercial now.
Did you escape button?
Yeah, I did. It didn't escape. All right, so, so that, kind of shows, that it is a serious thing. If you go to YouTube and type in laser pointer at airplane, there's a bunch of videos that, it's like they have 20, 30 incidents a month, shooting planes at airplanes, laser pointers at airplanes, and some of these guys get serious fines. I think one guy got 14 years in prison for doing it, plus a $200,000 fine. So it is a federal offense. Okay, this is, I don't know, I like Gary Larson. Peer pressure in the laser lab. Those are two guys that have eye patches. One guy doesn't. He's got both eyes. Good stuff. All right, so we've been talking about lasers, but we really haven't talked about what laser stands for. Laser is an acronym, and the acronym stands for light amplification. How is light amplified? Through the stimulated emission of radiation. So when you see the term laser, just remember that it's not actually a word, it's an acronym, and it actually is a good acronym because it actually explains how laser light is created. So light amplification through the stimulated emission of radiation. Lasers. Lasers are classified, and there's a bunch of subclasses that we're not going to get into because it kind of gets into the weeds, but depending on the industry that you're in, they do have little subclasses. But when we talk about laser safety, lasers generally fall into one of 5 categories. Okay? There's actually 4 classes, but there's one class has 2 parts, class A and B. So the classes are specified by an organization called LIA, the Laser Institute of America, in conjunction with ANSI, the American National Standards Institute. So these are actually standards. It comes from something called ANSI AZ. Actually, there's a Z136. There's also an A136.5. So depends on the industry which standards you're looking at. But these are the basic classes of lasers. So there's class 1, class 2, class 3A and B, and class 4. Class 1 lasers are lasers that are considered to be exempt. Okay? These are lasers that cannot hurt you. Now, most industrial lasers, which are multi-kilowatt lasers that can cut steel and do this kind of stuff, from IPG, this is kind of, pass this around. These are all class 1 lasers, and you might ask, it's like, well, if the laser is strong enough to cut through inch-thick steel, why is it considered exempt? Why isn't it considered dangerous? Because a class 1 laser is a laser that is enclosed in an idiot-proof container. Basically, you have an enclosure that you're denied access to. If you open up the enclosure, the laser shuts off. Okay? It's kind of like, if you have a big CNC machine, you have a big door in front, you open it up, usually the machine stops. So it's very difficult to hurt yourself as a class 1 laser. The laser that the students built in the back, when they built the enclosure, I made sure that it was a class 1 enclosure, so that you just can't hurt yourself with it. Okay. Class 2. Class 2 is considered a low-power visible laser of usually 1 milliwatt or less. Now, we do have some lasers in the back, the helium neon lasers that we have, little red gas lasers. Some of them are 0.95, which makes them what they call eye safe. Eye safe is still, it's more difficult to blind yourself with it, but it can cause problems. If you've ever been hit in the eye with one of those lasers, and I've been hit a million times, because students will take the laser and hold it up while it's on, and it's like wham, you hit in the eye. And you'll go home, you'll have a headache, but you take an Advil and it goes away. But it's like they tell you not to stare at a welder's torch or don't look at the sun. Same thing. It's just a bright flash of light that can temporarily impede your vision. But that's class 2. Class 3A. Class 3A are lasers that are rated from 1 to 5 milliwatts. Most laser pointers are class 3A. This is a 4 milliwatt laser, a red laser here you can see over here. That's about 4 milliwatts. Okay? This is considered eye safe. And basically, if it's viewed with a normal eye, okay, with unaided eye, it may cause injury if you wear glasses. Okay, it actually may help to focus the light more onto your retina, so it could be potentially dangerous in that regard. But again, it's considered eye safe, but if you go through the calculations, these 4 to 5 milliwatt lasers still exceed the maximum permissible exposure for retinal damage. So you don't want to get hit in the eye with one of these, even if it's considered safe. This laser here, and one of the things that concerns me about this, and I got this online, I think it was made in China, is any laser that you buy, I don't know if this one has it either, but any laser that you buy should have a laser warning tag on it, okay? This is required by the FDA. And of course, it's so small you can't even read it, but it says danger, you see that part. But it also tells the wavelength and the power, okay? And it tells the class. This should say class 3A. And I can't see it because it's so small. Anybody have good eyes? Magnify glass. But, you know, just be careful when you buy stuff that is not made in the United States, because it can exceed the FDA warnings because they don't really adhere to that. You know, this was actually purchased as a 5 milliwatt laser, and this is like 20 milliwatts. It's pretty bright. So, class 3A. Class 3B. Class 3B lasers range from 5 milliwatts to 500 milliwatts, and these can definitely hurt you. Okay, no ifs, ands, or buts about it. And we've got lasers here that do that. You know, we have laser pointers that are 500 milliwatts. So 500 milliwatts is just on the verge of what can cause fire. Okay, if you have a half a watt laser, you shine it on your hand, you'll feel it. It feels like a soldering iron. And if you focus that, you can definitely burn stuff with it. You can burn paper, you can burn wood. So class 3B requires certain use of danger labels. Typically doors are interlocked so that the laser turns off when you open the door.
So something like that, would that be considered like, I see people like doing the tattoo removal?
Tattoo removal is usually class 4 lasers.
Oh.
Yeah, so when you, yeah. Class 4, anything that's over 500 milliwatts, a half a watt, is considered a high-powered laser. And this can injure you, it can burn you. It's funny, you know, back in the old days, you know, people used to go around. You ever watch like Lethal Weapon and they're showing the scars? It's like, I got this one, I got stabbed, I got shot. Well, laser people, you know, go, hey, I got a burn hole here, I got a Nike swoosh on my hand. You know what the Nike swoosh is? If you're working with a carbon dioxide laser, usually infrared laser, you can't see it, and you only know it's burning a hole in you when if it hits you, it starts burning, and it takes a couple seconds for you to go, ow, and you go like this. So you get the hole that's burned, and then a swish as you're yanking your hand away. Yeah, so, you know, it's you know, kind of rite of passage, I guess, if you're an old laser jock. But anything that's a half a watt or more, okay, you know, we're talking 500 milliwatts up to 50 kilowatts, you know, those are class 4 lasers, and you have to have very rigid safety precautions put in place. And we're going to talk about some of those. So, class 1, 2, 3A, 3B, and class 4.
Do they have safety gloves that will not allow?
Yes, they do, yes. Matter of fact, it's on the next page. Not the next page, hold on, let me go back.
I did have a question
Yes.
before we go on. So even if a laser emits over 500 milliwatts, if it's in a full enclosed space, it could be considered a class 1?
Yes. Yep. And again, most class 1 lasers are lasers that are over, you know, they're hundreds or thousands of watts. You know, you just don't have access to it. So it's idiot-proof. So if we look at some of the control measures for class 3B and class 4 lasers, they fall into 3 basic categories. Engineering controls, administrative and procedural controls, and personal and protective equipment, which includes eyewear, clothing, and gloves that are flame retardant. Engineering controls. Engineering controls are basically anything like protective housings and panels that limit access to the laser. Interlocks, whether it's on a class 1 enclosure or even a room, like we have a room down at the end of the hall that has, I think it's got we had an 8-watt laser in there, it's not working anymore, but we have a 50 milliwatt frequency double diode pump YAG laser in there. So 50 milliwatts is still class 3B. So we have interlocks on the door, so if you open up the door, it disconnects the power to the laser and it doesn't work, so you can't hurt yourself. Beam attenuators and beam shutters. Attenuators and shutters, anything that you put in front of the beam, like this one here, This is an old neodymium YAG laser, but it actually has a shutter that is built in over here, so that when you're not using the laser, the shutter closes and you can't, the beam doesn't come out. Emission delays, filtered viewing optics. If you look at the laser that we built in the back, it actually has this greenish glass in front of it. That glass is actually an optical filter designed for the specific wavelength of a fiber laser. So even though you can see the beam coming, as it's processing the material, the light doesn't come through. So that part of the reason, this is a fiber laser here. This is a 40-watt fiber laser that one of my students built a couple of years ago. And the reason I don't turn this thing on yet is because it was built for display purposes. It actually works. And I want to turn this thing on, except this plexiglass is not safety glass. It's not tuned to the wavelength of the light that's put out by this. So I actually have some that I bought that I'm going to cover this with that green colored glass that will filter out the light, because you always get a little bit of leakage coming out from the fiber itself that's generating the light. So once we make that safe, then we can turn it on. Beam enclosures. Always, the rule of thumb is when you're working with a laser, always know where your beam is. A lot of times you have big 4x8 steel tables that you have an experiment on, and there's like a bunch of lenses and optics. Before I do anything, show anything to anybody, I mean, I'm wearing the goggles as I'm setting these lab experiments up. I always do a walk around of the table to make sure that there's no beams that may be reflecting off an optic that I'm not seeing. You always look around to make sure that there's no stray beams going anywhere, because somebody can just walk by and go bam, and whack in the eye with it. Don't want that to happen. Warning lights, emission indicators. Again, the laser that we built in the back has a little red light on the top that when you turn the laser on and it's active, it has a little light that shows that it is on. Controlling beam path, laser control area, beam stops. They actually have devices called, I might have one over here, it's called a beam dump. Beam dumps are sometimes when you're running an experiment, and you're reflecting light off of something, some of the beam has to go somewhere else, so a lot of times people will just put a brick or a cinder block, but they also have, for higher powered lasers, these boxes that are water cooled. It's called black box. And basically it's a hole, and it's got dispersive elements inside that scatters the beam with heat sinks, and sometimes those are also water cooled to absorb the energy. I used to have it over here, so I'm not seeing it now. So all kinds of different things. Anything mechanical that can be used to prevent access to the beam is important. Then there's administrative and procedural controls. There's a whole slew of things that you can do just to warn people about, there's lasers in this room. Like every door that we have here has a sign that says danger, laser beam. So as soon as you walk in, you know there's something going on. Most organizations also, if you're using lasers, you have to have a designated laser safety officer. Do you guys have one at your company?
No, we're too small.
Okay, so.
I mean, they might have them where they manufacture. But
Yeah. If anybody who's a company that's manufacturing lasers, there's always one, like a company safety officer. We have one on campus too. I think it's me. No, we actually have a campus safety officer who I imagine the responsibility falls on that person, but they always look to me. It's like, so, yeah, you're responsible. So, laser safety officer. The nice thing about laser safety officer is the organization, LIA, that does the training and certification is in Orlando, Florida. So if you're lucky enough to go down there in February, then it's not a bad week long down there. You do laser safety training, get certified, and everything's good. Standard operating procedures. Again, another administrative control. Limitations on use by class. Entry limitations for visitors. We have tours all the time. Little kids, elementary school kids come through here, and the first thing they're going to say is, can we see a laser and can we blow something up with it? So it's hard to show people, if you have a group of people, bring them into a dangerous environment because you're liable for their safety. You have to have the right safety goggles, all of the controls have to be in place to guarantee that they're not going to get hurt. Different warning signs for different types of lasers, education and training, service manuals. Like I said, you go to work for Coherent, you have to take the laser safety course, period. No any discussion. Same thing with New Firm. We're going in a couple weeks for a tour. They hire lots of interns from this program, and the first thing that they do as soon as they walk in the door is they spend a day doing laser safety training so they don't kill themselves. And then finally, protective equipment. Eyewear is probably the most important thing. We're going to talk about how do you spec out laser safety goggles. It depends on the wavelength and the power that you're trying to achieve. There's a whole bunch of different types of laser safety goggles as well, depending on what you're trying to accomplish. Laser safety goggles, for example, if you're working with an infrared laser that you can't see anyways, you might as well be, well protected, 10 times what the protective ability should be, so you over-design it. But if you're using like a high-powered visible laser, like we have an 8-watt green laser down the hall, and a lot of times, if you're setting up an experiment, you need to be able to see the beam, otherwise it's kind of hard to set up the optics. So they have laser viewing goggles that are transparent enough at that wavelength that light can come through it so you can see the beam when you're lining it up, but it has enough protection so that if it reflects off a surface, or something, you get a stray reflection, it will protect you from that. Won't protect you from a straight shot to the eye, but that's hopefully you're responsible enough to avoid that. Special clothing, gloves also, if you're working with infrared, materials that are flame resistant is always a good thing. Just a lot of times it always comes down to common sense. Like if you're working with a high-powered laser, you probably want to take your rings and your jewelry off because these things reflect. If you have, like the lab at the end of the hall, I had everything painted black in there so that nothing reflects off the wall, although we still have doorknobs and things that are reflective. But you try to minimize the danger when you work with lasers. Okay. Maximum permissible exposure. This is the important thing that determines whether you're going to be blind or not. Okay? Maximum permissible exposure limits indicate the greatest exposure that most individuals can tolerate without sustaining injury. Laser characteristics, and these depend on the maximum permissible exposure depends on the wavelength of the laser, the output energy and or power, the size of the irradiated area. Remember that equation for radiance? That's very important here. The duration of the exposure, is it a quarter second? Is it 5 seconds? Is it 10 seconds? Is it 20 seconds? How long, can your eye take that amount of irradiance? And then what is the pulse repetition rate? How many pulses, if you're working with a pulse laser, how many pulses can you take? Because even though the time may be in microseconds, it's pretty high in power. So how many pulses can you take? So in a nutshell, what we're looking for is whatever laser you're looking at, okay, you need to know what the irradiance is. That's why we did chapter 2 first, so that you can calculate and understand better what irradiance means. So if I take a laser and I shine it, what is the irradiance of that beam? You guys remember what irradiance is? What's the definition of irradiance? I said calculate the irradiance. What two things do you need to know? Area and power. Okay? Watts per square centimeter. You need to know what the area of that beam is. Okay? And what is the power that is in that area? So power divided by area, power density. So, and that determines well, we're going to talk about, but the optical density of the glasses that you're using to protect your eyes from that. So, this is a chart that I pulled out of the ANSI Z136.1 back in 1993. It really hasn't changed much. Like I said, they have added some subclasses of lasers that didn't exist back then. But really what it comes down to is the wavelength of light and the power levels. Okay? For all the lasers that we use in this class, we're only concerned with visible lasers. We have red, green laser pointers, maybe some violet ones. Visible lasers all fall under the same wavelength range. If you look at the laser type over here, and then the wavelength, okay, anything that's between 400 nanometers and 700 nanometers, 0.4 to 0.7 nanometers, okay, it has the same maximum permissible exposure. Now, if you look at this, 2.5 times 10 to the minus third watts per square centimeter. What is 10 to the minus third? Million, okay? So, regardless of what the visible laser is, if you can see it, then in order for you to protect yourself from that, its irradiance cannot be more than 2.5 milliwatts per square centimeter. And that's only for a quarter second. Why a quarter second? What's the reason for the quarter second, Dave?
Aye.
The blink response, yeah. So in a quarter second, most people, you know, if you get hit in the eye with a laser, your natural reaction is within a quarter second, you can blink and turn away from it. And that should be enough to protect you if the irradiance is less than 2.5 milliwatts per square centimeter. So, let's do an example. Okay? We've all seen the power meter, it's plugged in. Okay. We have a laser, we have a power meter. Okay? We're going to shoot the laser into the power meter. And because you can't see it, I can. I'm shooting this in, oh, look at that. We have, even though this is supposed to be a 4 milliwatt laser, I'm reading 8.9, let's say 9 milliwatts, okay? So for this laser here, power is 9 milliwatts. Okay? Now, if I look at this laser again, if I went boom, and you know, zap myself with it, okay? How big is that laser? What do you think? Have we got a ruler? Usually it's between 1 and 2 millimeters. Let's shoot for the, he's got, of course he's got a ruler. He's got a briefcase, he's got a ruler in there. Old leather one too, I used to have one of those. That's okay. So these are usually about between 1 and 2 millimeters in diameter. So you basically have a spot that is diameter D of, so let's say 2. Okay, make the numbers easy. 2 millimeters. Okay. The bigger the spot, by the way, the less the irradiance, so the safer it is. So if you want to protect yourself, you know, one of the things you can do is diverge the laser beam, spread it out so that it spreads the power out as well. But if we have a diameter of 2 millimeters, what is the area of that circle?
3.14
Pi
times
times,
0.01.
but what's the general equation? Pi r squared?
Pi r is 1, so
Pi r squared, or I like to use pi d squared over 4, because the numbers are usually given as a diameter. So either you can cut it in half and use the radius equation, or this, the same thing. So the units that we want usually are milliwatts, watts or milliwatts, because it's given in milliwatts, per square centimeter. So whatever our area is, we want to make sure the units are in centimeters. So if we've got a diameter of 2 millimeters, okay, that's the same as saying 0.2 centimeters, okay? So if we take this now and we plug it into our area equation, the area of that beam is pi times 0.2 centimeters squared divided by 4. When you square this, you square the 0.2, but you're also squaring the centimeters as well. So you get 0.2 squared times centimeters squared. And if you do this math here, what do you come up with? What about your calculators? Let's see what we get.
.0314.
0.0314, what's the units?
centimeters.
Centimeters squared. I ask that, and I do this all the time, because inevitably on a test or a quiz, somebody's going to use millimeters, and they're not going to come up with the right answer. Always make sure you show your units. Okay, this looks about right. Anybody concur with that? Okay. So we have an area of 0.0314 centimeters squared. So if we plug that into our irradiance equation now, irradiance is equal to power over area.
Was that divided the area?
Yeah, power divided by area.
If you divide the 4, it's
Oh, yeah, is this divided by 4 where we calculated it?
I divided it by 4.
Okay. Okay. So if we plug our numbers in here, we have 9 milliwatts divided by 0.0314 .030.314 centimeters squared. Notice our units will be in milliwatts per centimeter squared, so what's 9 divided by 0.0314?
8.286.
Say again?
About 0.286.
I-
0.286.
Point two, sure.
Yeah, 1.0000286.
Oh, in,
286.
Okay. I know what's happening here. People are plugging in 10 to the minus third here, plugging in.
oh, in
Yeah,
milliwatts.
So just
Yeah.
leave this as milliwatts. If we leave it as milliwatts, your units will be milliwatts. So if I just say 9 divided by 0.0314, I get 286 milliwatts per centimeter squared. Okay? 286.6 milliwatts per centimeter squared. Huh. Over here, and this, by the way, is a diode laser, so it has a maximum permissible exposure of 2.5 milliwatts per centimeter squared, meaning anything greater than 2.5 is going to cause problems. Okay? 286, 2.5, that's 100 times more than what's allowed. So I will not shoot this into my eye just because of that. This will hurt. This will cause problems. You know, you go to your eye doctor and they show you pictures of your retina with a little hole in it. So there's a problem. So again, as long as the laser is visible, and this is the only thing you have to worry about. When we get into infrared lasers, okay, notice how we look at 10 seconds, 600 seconds, and 3 times 10 to the 4th seconds. These are empirical values that were developed by people at ANSI who were looking at biological effects of infrared lasers. And the reason that they show it as 10 seconds is, first of all, visible light, we'll show this in a second, but visible light is probably the most dangerous to your eye. And you think, well, you know, if I use a high-power carbon dioxide laser that can cut steel, will that blow a hole in my head? Probably. But in terms of your retina, you know, most of the light that from infrared and ultraviolet is absorbed by the cornea. Okay? It never really gets to your retina. It'll blow your cornea out. But it won't get to your retina because, you know, the same reason that carbon dioxide laser just sits there and burns a hole in plastic, you know, it's like a brick wall. It just kind of sits there and cooks, you know. You can have your lens replaced. You can't replace your retina. So the visible light is the stuff that gets through the cornea, gets through the lens, and gets focused onto the back of your eye. So this is the stuff that can cause permanent damage. So if we look at different parts of the eye, okay, that's a nice picture of the eye. Your cornea is this layer on the outside here. So actually, anybody ever have LASIK surgery? No? LASIK surgery?
Yeah, I would love to though. I just don't have the $5,000.
Yeah, well, it's actually come down, although the fact that it's cheaper now kind of worries me.
Yeah, we've got lasers, let's do this.
Yeah, I'm up for that. Who wants to try?
I had it done. I had it done like 10 years ago, 12 years ago, I think. It did cost $5,000.
Yeah.
But what they do, when you have laser surgery, you go online, you can go to YouTube, and they have videos of this whole procedure being done. When I had it done, back in the old days, they used to take, there's a little layer of skin over your cornea. So they have this little device called a radial keratome. It's basically like a suction cup with a blade that kind of scores like a semicircle, like 270 degrees or so. And they suck it on your eye, and then they go like this, and they slice a flap in your skin over your cornea. They peel it back, and they hold it there, you know, which exposes the cornea. And all they do then is they basically use a laser to shave layer by layer off your cornea. So if you have, if you're nearsighted, for example, that means this is too rounded. So all they do is they shave off layer by layer, you know, they flatten it out a little bit. And what that does is it pushes the focal point back to where it needs to be. And when I had it done, it's like every pulse removes a certain layer. They use Excimer laser, shortwave ultraviolet lasers for doing this because the process is different. When you use ultraviolet light for biological materials processing in general, ultraviolet light processes materials differently than infrared. Infrared is a heat process, a thermal process. Ultraviolet light is an ablation process where the wavelength of light basically breaks apart the molecular bonds that hold the tissue together. So if you're getting blasted, you know, with a number of pulses, each pulse basically ablates or flattens out, removes a certain layer of tissue, thickness of tissue. So depending on your prescription, they just flatten it out a little bit. And then in my case, they take that little flap it back over, get a little squeegee, you know, put it over there, and they stick these little bug-eye glasses on you for a day, just so you don't poke yourself in the eye. And within a day, the skin readheres itself. And the amazing thing is, as soon as you get up off the table, it only takes like 10 seconds to do this whole thing. As soon as you get up off the table, you know, I remember being able to read the doctor's name on the door across the hall. It's like, wow, I could never see that before. It was pretty cool.
Because you're awake when they're blasting your
Oh, yeah.
eye blazing.
Yeah, but there's no nerves in your eyes, so you don't feel it. You can't feel a thing. The only thing you feel
It's terror.
is it's terror, yeah. No, the only thing you feel is they have this clamp that kind of clamps onto your eyelids, and then they turn the thing and it opens up your eyelid, just holds your lid open like that, so that you don't blink while you're having the surgery done.
Surely they have
And that's
something
the most.
so you don't twitch.
Yeah, and well, actually, it's interesting. The twitching part, they have laser radar that tracks your twitching. So if your eye moves, the laser moves with it. So it's pretty sophisticated. But just the clamp that's holding your eyelids open just feels weird, you know? It's just it doesn't hurt. It's just
on YouTube, the whole thing.
yeah.
Wait a minute, you said there's no nerves in there. How come I watch so much focus over the eye?
Good question.
I guess the area around it when
The area around the muscles around it,
Yeah.
you'll feel it. But no, when you do laser,
Not
So-
more. There's not really nerves. I think it's right in the center. The area around it is a little bit more
Yeah,
more
so I mean, the
sensitive.
lens part, the cornea, there's no.
Yeah, the whites of your eye, I think,
Yeah,
have some
the whites of your eye,
nerve
because you can
impingement.
see there's muscular tissue inside there that you call it sensory perception. But the cornea doesn't, you know, I had that done, I think it was 12 years ago I had it done, and, you know, I've had 20/20 ever since.
Has it changed?
Hasn't changed, no, it's actually been pretty good. So if you look at the eye, you've got the cornea, your pupil is the opening of your eye, and that changes depending on if it's light or dark. Your iris is the thing that opens up and closes. And then you have the lens. Now, interesting thing now is a lot of people who have cataracts. My mother just had this done. If you have cataracts, they just yank that whole lens out, throw it away, and put a synthetic lens in there with the right prescription for whatever prescription you have. So you don't need glasses anymore. So my mother always wore glasses. She just had cataract surgery, and now she doesn't need glasses because she has fake lenses put in there. Pretty cool. But if you look at the eye, you've got this gel part in the middle here, okay, which is called the vitreous gel. It's like the goop inside your eye. The macula is where the vision center is, and the optic nerve. So when you are looking at laser light, unlike looking at an image of something, if you're looking at an object, okay, what happens is your lens actually converges, diverges, and forms the image of that object, whatever it is, on the back of your eye, and your retina picks that up, and that's how you see. But when you have collimated light coming in, and this is the problem with lasers, okay? If you've got perfect 20/20 vision, if you get collimated light coming in, okay, it's not divergent, straight coming in, that lens, just like a magnifying glass, will focus directly on the retina, okay? And that's why lasers are so dangerous. If you have a white light source, white light sources diverge, okay? Lasers are straight, okay? Now, if you look at this, there's two types of vision. There's myopic and hyperopic. So myopia, if you're nearsighted, that's called myopia. What does that mean?
Apparently it means your lens is too bulgy in the middle.
Yeah. So if you look at your eyeball, right, and you have your lens, okay, if I have laser light coming into that, or if you have light coming in, let's say, for people who are nearsighted, okay, let's say if that light comes in, okay, nearsighted, it causes the light to come to focus early, okay? So you end up blasting the vitreous fluid inside of your eye, okay? If you are hyperopic, if you have farsightedness, hyperopia, okay, that means that the light that comes in is actually focused somewhere over here. Okay, it focuses beyond the retina. Okay, not so problematic. When you have glasses, I mean, ideally you're going to focus right on the retina. You have good vision. So if you're nearsighted, you wear glasses, and this is the focal point. Okay, if you're trying to correct that, you want to push that focal point back over here. Okay, all that means is that this lens is too round and it's focusing too fast. Okay, so the idea is to flatten that out somewhat. Okay, to push that focal point back. So when you have laser surgery, LASIK, okay, that basically just takes that focal point and pushes it back onto the retina by flattening out this your cornea. Now, the other alternative is glasses. So if you're nearsighted, you basically have a negative lens there. So what it does is spreads the light out a little bit so that when your lens actually focuses it, it compensates for that short focal length. If you are farsighted, okay, it's the other way around. Your lens is not round enough. Okay, so you have to add a positive lens to the front. That's why if you see people who have, some people you have thick glasses. They're thick glasses that make their eyeballs look huge. You know, those are people who are farsighted, because when you have a positive lens and you put it in front of your eye, it actually acts like a magnifying glass, and it makes it that your eyeballs look big. So, anyways, just.
Can they still fix that with LASIK though?
Oh yeah,
Can they
yeah,
just round
actually.
the outsides?
Yeah, they used to not be able to, but the way they do this now is, so if you have your corneas like this, and you're farsighted, so they have to make it rounder, what they do is they put a mask on here. So you mask off the front portion, and you let the laser light hit the sides. So what that ends up doing is shaves off portions around on just the side parts, so that it ends up making your eye more round. So that's kind of cool. All right. So I'm not going to go through this part here. This basically talks about the different parts of the eye. You know, it's interesting reading, but it's not a biology class, so read it if you want. This is the another one of the important slides. This shows what parts of the eye are sensitive to what parts of the spectrum. If you look at the top picture, okay, visible and near infrared, okay, and also middle ultraviolet radiation is absorbed mainly by the cornea. So if you remember anything, the UVA, and UVB, very heavily absorbed by the cornea. Nothing really gets through to the retina. So, you know, the UV light will cause damage to the outer part of your eye, but hopefully won't, you know, impact your vision. Same thing with the infrared. Okay, the infrared actually gets through a little bit, near ultraviolet and infrared from 700 to 3,000 nanometers. Okay, penetrates the cornea, okay, but it gets absorbed by the lens. Okay, so this will affect your cornea. I mean, your cornea. This will affect the actual lens, but it's the visible light, okay, that comes in that actually gets focused onto your retina. So the three different wavelength ranges there that affect the eye. These are some pictures. I don't know how well you can see that, but this is a hemorrhage of the vitreous humor in the top. So if you get that light focused into the center of your eye and it blows out some of your gel, okay, that's kind of what it looks like. This is what a retinal burn looks like. Okay.
Wait, is this circle pupil?
This is the back of your eye. So if you go to you go to the eye doctor and take a picture of the back of your eye, okay, that's what happens when you have a burn on your retina. And this actually, I take that back. This looks like the burn right here. Okay. And this is a corneal burn. So if you burn your cornea with an ultraviolet laser, it's kind of hard to see what you're looking at there, but you can actually see some scar tissue on the cornea. And this is what I was talking about before. When you take a laser that's collimated, it will come to focus on the back of the eye because it's collimated. Compare that to if you're looking at a lamp or an image of something. Okay, the light, because it's diverging, will get imaged by the lens okay, focus to the center of the eye, and it's expand back out again so the image is inverted and put on the back of your eye, and your brain actually flips the image back around. Yes?
If the collimated beam was as wide, say, as an incandescent bulb, say, wide, would...
Good question. So if I take this and I shoot it into my eye, my pupil in this kind of light is probably about 5 millimeters dilated, okay? This is about 2 millimeters, like we just did the example. So all of this, because it's collimated and small, you're taking all that light and you're concentrating it, and all of it's getting through the pupil, you know, being focused on the back of your eye. If you have any other light source, like any extended light source that kind of diverges, like this here, okay, not all of that light is getting into your eye, which is another problem with lasers, is that because they are small, they are very intense, and chances are if you get whacked in the eye, all of it's going to go into your retina. Even if, and the thing we're going to do this afternoon for lab, the laser safety lab, is what if I took this laser and I shined it, okay, I mean, we said it was like 2 millimeters up close. How big is it on that wall over there? What do you think? Look at
Twice
that.
the size.
Twice the size, maybe 4 or 5 millimeters, you know? So if your pupil is, let's say, 5 millimeters, fully dilated is usually about 7 millimeters. If this is at a distance, you know, if you go, you know, 100 feet away, okay, it may be this big. You know, even though it's still pretty tight, you know, it may expand out to several centimeters, okay? Of that, what's going to hurt you? You know, if your pupil is this small and the circle is this, the area is this big, you're only letting a small portion of it into your eye. Okay, so what, and that's where the irradiance is important. Okay, if you know what the irradiance of that spot is that you're focusing on to whatever, okay, that is what determines what the power density is. And then if you take your eye, which is just a small hole, and take a portion of that, the irradiance is still the same, but because you've spread it out, the irradiance has dropped down. So in the lab today, what we're going to ask is, what if we had like a 25 milliwatt laser, like one of these things, you know, and you know, you shine this on somebody 1,500 feet away. Okay, what's going to be the damage? How do you figure that out? Is it going to cause a problem? Is it not? So you start thinking about that. How would you figure that problem out? So this is an example similar to what we just did. Okay, as a matter of fact, it's actually very similar. If we have a laser pointer, let's say 670 nanometers, which is this red guy, okay, and let's say it puts out 3 milliwatts. Okay, this is considered eye safe. You know, remember class 3A, 1 to 5 milliwatts. The laser beam enters the eye with a 7 millimeter fully dilated pupil, which means all the light gets into the eye. That's what I'm saying. Determine whether the beam from the laser exceeds the maximum permissible exposure for 0.25 seconds. Okay, well, let's do the math. If we plug in our numbers, okay, we've got pi d squared over 4, 7 millimeters, let's say that it just fills that whole pupil. Okay, 7 millimeters is 0.7 centimeters, so we just convert it to 0.7 centimeters. So pi times 0.7 squared divided by 4 gives us an area of 0.385 square centimeters. If we take that now and we calculate the irradiance is power over area. 3 milliwatts divided by 0.385 centimeters squared gives us 7.8 milliwatts per square centimeter. Okay, 7.8. Even though this is 3 milliwatts and is considered eye safe, 1 to 5 milliwatts, class 3A, we're still exceeded the maximum permissible exposure of 2.5 milliwatts per centimeter squared by a factor of 3. Okay, so this can still cause problems if you look at it for any extended period of time, more than a quarter second. Okay? And even at a quarter of a second, you know, it may or may not cause permanent damage, but it'll definitely, you know, you ever look at a bright light, welder's torch, and you go home with a headache, and it takes you like a couple of days to recover from it. Same deal. Okay. Classroom activity. In the last few minutes, I want you guys to do this one here. Let's say we have a helium neon laser. Okay, 633 nanometers. The only thing you need to read from that is 633 is visible. So what's the maximum permissible exposure for a visible laser? All visible lasers? 2.5 milliwatts per square centimeter. Beam enters a human eye with a fully dilated 7 millimeter pupil. Okay, so you got your pupil is this big. Okay, but now we're saying that the diameter of the beam, when it comes in, the beam diameter is only 3 millimeters. So you got 7 millimeter pupil, 3 millimeter beam, so all of it's getting into your eye. Okay? Determine whether the beam can exceed that maximum permissible exposure. So in this equation, this problem, what are we going to use as the beam as a diameter?
3 millimeters.
3, right? Because it's all getting in the eye, yes. So calculate the irradiance, power divided by area, for the situation. And tell me if it exceeds the maximum permissible exposure. And if you can do this problem, then you'll be more than likely to be able to do this on the next quiz. That's called a hint. This is the kind of stuff that I want you guys to be able to do. Okay, simple first order stuff. Tell me if I'm going to get blinded by this laser. Because if you are, then we can design safety glasses so that you don't. Or speckle out. And while you're doing that, let me grab some safety glasses. You got a number yet?
42.49 milliwatts per square centimeter.
Okay, anybody else get that? Okay.
Because I took the 5 milliwatts,
Yep.
divided it by diameter. The diameter divided by 4.
Would you calculate the area though?
Yeah, the
Okay.
area was .236. So you take the watt, or the milliwatt, 5, divide that by the area. Right?
Yep. So let's do this together. Okay? Area, pi d squared over 4.
Yep.
Okay, so we have a 3 millimeter diameter, so this is 0.3 centimeters. So pi times 0.3 centimeters squared divided by 4. You guys do this? What'd you get for a number?
0.0706 centimeters squared.
0.0706.
706
Okay.
to 0.071.
Throw it in there. Okay. So 0.0706 centimeters squared. The radiance is equal to 5 milliwatts divided by 0.0706 centimeters squared. If you calculate that, you get, what did you get?
Oh, yeah.
42.49.
Milliwatts per centimeter squared. So does this exceed the maximum permissible exposure?
Yes.
Yes, so it does. So don't look at that laser.
I figured out what I did wrong. I did a square.
You didn't square it.
That area, yeah.
All right, so in the last couple of seconds here, I just want to show you what we're going to be doing next class. When you buy laser safety goggles, oh, look at that, it's in the wrong box. Laser safety goggles are dependent on two things. The power level of the laser that you're using, which determines something called the optical density, and the wavelength. So if somebody hands you a pair of goggles, and they say, you're working with a red laser, you know, here's a pair of green goggles, always look at the goggles themselves. This one actually, they usually always show the wavelength. So ruby, it says ruby, it tells you the type of laser. Ruby laser, 694.3 nanometers, and it has something called OD, OD6. So this is for red lasers, okay? And usually if you see blue, a blue goggle, it's for red, it blocks the red. But it's got a reference called OD. OD means optical density, and this has OD6. What that means, and we'll show you how to calculate this next class, but an OD6 means if you take that number and raise 10 to that power, 10 to the 6th, that's the factor of how much this will knock the light down. So 10 to the 6th is what? 1,000,000, right? So light of this wavelength will be knocked down by a factor of 1,000,000. So if I have 1 megawatt of, hopefully you don't, 1 megawatt of light coming in here, you'll have 1 watt coming through. Now, if I have, 100 milliwatts, or 1,000 milliwatts, say I have 1 watt, 1 watt of light coming through here, I divide 1 watt by 1,000,000, I get a microwatt, okay? Which is usually sufficient. But depending on the irradiance of the beam, that's what determines the OD that you need to protect yourself from that. This also shows OD5 at 632 nanometers. So for the two types of red lasers, okay, this is OD5 at 1 wavelength and OD6. OD5 it knocks it down by a factor of 10 to the 5th, okay, 100,000 times. So always look at the OD number for those. This here, these are goggles that are designed for infrared. Okay? Again, right on the lens, notice the green tint to these. Okay? On the lens it says between 190 and 450, which is ultraviolet, and between 800 and 2,000 nanometers, which is infrared, this has an OD of 4. Okay? So for both ranges of wavelengths, this will knock the light down by a factor of 10,000, okay? Which may or may not be sufficient for what you're, the power level that you're using. But if you calculate the irradiance, okay, and then divide it by that OD number, okay, if it brings it down below 2.5 milliwatts per square centimeter, or whatever the chart says for that particular wavelength, then you should be okay. Now the one interesting one that I wanted to show you was this here. Okay, these are
Welders.
like welder's glasses. Yeah, these are for very high powered lasers. This shows an OD9 at 1060 nanometers, just in the infrared part of the spectrum, just beyond the visible. This is OD9, which is 10 to the 9th. So this knocks it down by a factor of 1 billion. Okay. Yeah.
2 questions.
Yeah.
The first question might have an obvious answer, but are there a pair of goggles that would work for pretty much any wavelength that you'd work with, or do you have to have goggles that will work for a
They're
specific?
pretty much designed for that wavelength.
Okay.
Yeah, so it has to have absorption characteristics that are wavelength dependent.
And
I mean, if you wore just, I take that back. If you had like neutral density filter that basically has absorption across the spectrum, a really dark pair of sunglasses, you have to look at the spectral absorption charts for that. But yeah, you could do that. But then you would block all the light out, you won't be able to see anything.
And then the other question is, so when they specify a wavelength, at that specific wavelength it's had its highest OD, how does that affect the wavelengths that are close to it?
Well, by this one here, I mean, if you looked at the red laser one, it was OD6 at 694 and OD5 at 632. So if I'm using a red diode laser, which is somewhere in the middle there, I can imagine it's probably going to be between OD5 and OD6. So you kind of like, you interpolate it that way. But yeah, I mean, they do have a range that you can use these at. And this actually is in the wrong case. This was supposed to be the viewing goggles. When you're working with green light, it actually has an orange tint to it. And the orange tint, the ones I have an OD of 2.4, which is just over 100. And usually using these with pretty high-powered green lasers, which doesn't block out enough light to make it safe, but they're called viewing glasses that blocks out enough so that you get a stray reflection and it won't hurt you. Okay. Any other questions?
At 42, it should be 70.8.
Yeah, that's 3 divided by 0.076.
Oh, so this is wrong? Okay.
Yeah, that's
Who can we blame for that? So what was this answer?
70.82.
So it's even worse. 70 point what?
82.
Milliwatts per square centimeter. All right. So it's even worse than we thought. Okay, does anybody have any questions before we go into lab? For those of you who have Thursday lab, take 10, come back, we'll get going. For those of you who don't, we'll see you then.
Yeah, I was gonna ask about Tuesday